for opening our eyes to the miraculous application of PGM. Well, thank you for bearing with us. Your stomach are complaining. As close to lunchtime, we prepare some refreshment outside. But before we eat the real food, let's have some food for thought. So think about the environmental pollution and climate change are the daunting issues facing mankind. It's also an issue related to whether on this blue oceanic earth, how can we give birth to the next generation as well. PGM in the human concerted efforts, it has its relevant role. So let's welcome the founder of Jiping Technology and CTO, Zou Yumin, to do a presentation to give us some insights. Mr. Zou, thank you. It's my pleasure to represent my organization, Jiping New Energy, to talk about PGM, its future development. Of course, I'm going to do a recap of our history as well. Just now, Mr. Chen Wei from Anglo America gave us a very big picture to talk about the application of PGM. Me personally, I'm not as knowledgeable as him, so I'm going to talk about it from a narrow perspective, from the electrochemical and chemical perspective. This is something I'm familiar with. So for us, we are the first one that can mass produce the kilogram level of a catalyst used for the fuel cell battery and water hydrolysis. We can produce catalysts at that level. So we have two sites. One is Anting in Shanghai. The other one is for Shanyi in Guangdong province. So the Anting in Shanghai, for that site, we have a headquarters, R&D center, production facilities, and in Guangdong, so it's mostly a production base. For cathode and anode, and also with carriers and without carriers, so you find the platinum and also the, for example, iridium oxide, water hydrolysis. So end of last year, ever since then onward, so we joined on the, for example, the business of for example, in water hydrolysis about the precious metal coating business, something we have exposure to. Aside from producing catalysts, when we go to the market, it turns out that it's important to work with the downstream customers. So that's why we provide catalysts. At the same time, we can assist our customers to do the slurry and to do the testing. At the same time, we can help them to do the CCM as well. As customers' specifications and their working conditions are different, so we are going to provide some solutions targeting their needs. What we provide is a one-stop shop solution. So we provide a slurry for the catalyst and the CCM, and also to make sure that we can make sure the customers can utilize our solutions.
So the slide shows you an overview of our catalysts. It includes fuel cell catalysts, PEM hydrolysis, as well as alkaline hydrolysis. As you can see on the slide, we can do all the way from 40% to 100% in terms of the catalyst that we make. For cathode, we usually use 20%. Of course, we suggest that you choose something of your favor. If you want to do something that's anti-polar, we suggest that you use like carbonated. But if you want to be more protective, we would suggest that you add iridium oxide. In terms of PEM water hydrolysis, of course, we use iridium oxide. Of course, we add platinum, and later on, I'm going to tell you why we did such addition. In terms of alkaline hydrolysis, mainly we use precious metals. We use mostly nickel and more precious metals. So in terms of the catalysts that we make, all of our catalysts include precious metals. This is the slide showing our production capacity, of course, depending on different scenarios, because market changes as well. In particular, the market with regard to water hydrolysis changes a lot, with a lot of new industries coming to battlefield or coming to the market. For the platinum, every day we produce 5 kilograms, and our goal is to reach 10 kilograms per day at the end of this year. As for iridium oxide, currently we produce 300 grams per day, but we'll expect to increase it to 1.5 kilograms per day at the end of this year. For PT Black, 500 grams currently, and we want to increase it to 2 kilograms per day at the end of this year. Of course, the PT Black has the wide applications beyond water hydrolysis. As for platinum alloy, this is something that's growing more slowly in China. Speaking of the industrial application of PGM, I'll just say a few words about how it's used in the chemical industry as well as in the electrochemical industry. In terms of its applications in the chemical industry, as early as 1965, someone called Wilkinson Catalyst from the UK. Almost at the same time, there was another person, also very well known, called Visca Catalyst. So the two did hydrogenation and hydroboration as well as hydrosylation and hydroformylation of alkanes. So they did all kinds of chemical reactions, in particular with regard to hydroformylation. In the double bond, there is another group added for the downstream. They connect as a starting material. So in the two bonds of hydroformylation, aldehyde was added. About several decades later, someone from UCLA called Grobskalus, he discovered some catalyst that's able to be used to produce polymer, and he actually found the RU for producing polymer, and he won the Nobel Prize in 2005. So all these show the application of platinum in the chemical industry have grown by leaps and bounds within a short period of 3 decades. This slide showed you application of platinum in electrochemical industry. Primarily in 1968, someone called Henry Beer from South Africa, a scientist from that country, identified ruthenium oxide. And by the way, ruthenium and radium oxides are both very special catalysts. They're endowed to us by God. They represent the biggest gifts endowed to us by God. Why? Well, at least up to now. Why? Because the two oxides, they can conduct electricity. For radium oxide, they have 1/10 of the electricity conduction capacity of iridium. So out of all the oxides, iridium oxide is just very special. So it's the best for electrolysis or for electrocatalyst, because if it doesn't conduct electricity, it can't serve as catalyst. So iridium oxide and ruthenium oxide, they changed the industry, because in the past, people use graphite. Graphite itself is dissolved or absorbed. That's why the two oxides, they are called dimensionally stable, because they are different from graphite. Because graphite, if you lay them on the ground, they become smaller and smaller over time. However, the two oxides, they're just stable. So for me, I have done a lot of experimentation myself. I use the two oxides in my plants, in my factories a lot. As early as diaphragm technology all the way to membrane technology, a lot of things have happened. So people have this urgent demand to use platinum-based materials, including platinum, and in particular, platinum and ruthenium. Of course, different companies have their different inventions. Another thing is about hydrolysis. Hydrolysis is very similar to other area. It's just that the cathode, for example, the collection of copper anode, there must be oxygen generated. But back then, we didn't have such thing as iridium oxide. As a result, you see that such application have widened the scope of application for PGMs. And I am confident that in the future, we're going to see many more catalysts of similar value. Next, I'm going to present to you something that I, together with my team, developed ourselves. It's very interesting. It's water hydrolysis of 15% of hydrochloric acid. Why are we doing this? Because hydrochloric acid is something used by a lot of chemical companies, including Dow's and DuPont. So they have wastewater. It's really complicated to deal with this wastewater. You have to put them through comprehensive treatment, and then you have to bury this wastewater underground. So by accident, we found that rhodium sulfide doesn't or will not be damaged. Of course, it's very good if you use platinum. However, plant disappear as long as there is one disruption. So the identification or such a discovery is very good discovery. Later on, together with my team, we did catalysts and we invented other things. They were first used in Germany and then, or they have been used in Yanhai and in Shanghai of China. In addition to electrolysis, of course, what's next is something of equal importance. For Jiping, currently our business covers this area, that is fuel cell and water hydrolysis. As for this thing, as I mentioned before, that we invented rhodium sulfide. This electrolyzer is very special because on the cathode uses rhodium oxide, but the anode is called DSA, is identical to the cathode materials. So this reaction is best in that it serve three purposes with one reaction. What does that mean? You turn waste liquid into useful chloride using hydrochloric acid, and chloride is just the starting material of a lot of chemical reactions for producing chemicals. So chlorine is very useful. What's more, electricity pressure can be lowered as well. This slide showed you the status quo in China because the slide is called Restart of the Hydrogen Industry in China. About a couple of years ago, this industry was just at the very bottom. Later on, Toyota led the entire industry to a better place, in particular in China. But there is a very important reason. So over the past 5 to 6 decades, oil or petrochemicals, basically every country, people just want to get rid of the reliance on oil. So fuel cell together with hydrogen represent the best combination to achieve that goal. Of course, we also have requirements from carbon neutrality. And recently, we found that hydrogen is actually a very good method to store energy. So it's a very good chemical for energy storage. What does that mean? So for any battery cell, if you lay it idle, whether you use it or not, electricity leaks from such battery. However, if you use hydrogen, then it doesn't leak, which is very important element. What's more, when hydrogen production is combined with fuel cell, people identify something that mutually reciprocal. In particular, there is a cycle, as was mentioned by a previous speaker, Mr. Chen, that precious metals, they do not disappear. If you finish using them, you recycle them, and then you can reuse them. As for other reactions that do not include precious metals, this is not a reality. This is not possible. So instead of examining the reserve of precious metal on us, when you use precious metals at certain time point, you can recycle them. As a result, precious metals, they're expensive, but every coin has two sides. Because they're precious and because they're expensive, it's very easy for you to recycle them. That's something that I need to highlight. There's another thing. When we recycle precious metals, and there is something called leasing. So I was in Italy. I worked in Genova of Italy for some time. So I know that all of their DSA anodes, they lease to their clients. So there are clients that will use these electrodes provided by this Italian company. After they finish using them, they return these electrodes to this Italian company with the rest of the monetized. This is just similar to the leasing of car batteries. As a result, the cycle runs smoothly. There's another thing, combining fuel cell with water hydrolysis, and this process is called unitized regenerative fuel cell. For URFC, basically for one electrolyzer or one MMA can be used for either water hydrolysis or for producing fuel cells. Why? Because power costs differently during daytime and at night. So at night, I can use power or I can use electricity as it's cheaper to produce oxygen and hydrogen, and such oxygen and hydrogen can be supplied to other areas. In the meantime, thermal is produced or heat is produced, and during daytime I will discharge or I will release electricity, as electricity is expensive during daytime. As this way, a lot of new applications can be come up with, in particular for people from different companies. You can think of how to use this to invent some new industries and add or expand applications of PGMs. In the fuel cell stack or in the fuel cell vehicles, what's critical, what's center here is the membrane electrodes, because they represent the source of power. And in the membrane electrodes, the catalyst is at the very center. So if you can find or if you can achieve technical breakthroughs on the front of catalysts, that will have a huge impact on the industry. So next, I would like to talk about how we do testing of these catalysts and how we manage to know which catalyst is better than others. This will cover both tests by us as well as tests conducted by our clients. So let's just walk in. And recently, our clients said they love 70% PT catalyst. Why? Because if you use 70% PT catalyst for the same materials, the cathode is very thin. As a result, for oxygen dissemination, and the speed of oxygen dissemination will become faster. So on this slide, I am presenting to you a comparison of products from Jiping as well as the commercially available iridium. They look the same or they look more or less identical. However, if we take a look at the quality properties and activity differences,
that's the difference between 0.25, 26, or 0.19. So why did I tell you that I'm so surprised to find this XRD? So XRD curve, it turns out at first glance, there's not too much of a difference, but if you're trying to enlarge the one from the left-hand side, please look at this flat line. There is a peak there. Seems like a flat line. It's like just the shoulder, and that there is a peak. I think the peak area indicates there are some oxide, so there will be a platinum oxide there, so affecting its performance. Think about platinum. It's a good catalyst, but you have to reduce it through action first. So, but if you oxidize it into the 4 valent ones, it cannot go back to the most effective catalyst platform, platinum. So on the right side, you find that this is a cobalt and a platinum. We have done some comparison between what we have and another company. You find that for their solution, they will have a cobalt oxide. So based on the alloy between platinum and cobalt, there will be different phases being divided. So that is going to affect your per quality and per unit activity as well. So given that such a catalyst, its activity is not as great as the one indicated by the blue one. It only enjoys the 36% of the activity level of the blue line. So what does this line mean? It means that our 50% versus imported 50%. So you find that actually in the accelerated square-shaped wave test, you can find difference. So the imported vendor, they have a huge and very fast degradation. Why is that the case? On XRD, it turns out their particle size is 2.5 to 3.0 nanometer. Given the size of that particle is not very appropriate for using the oxidization of something. So think about like a platinum particle is like the one indicated by blue, and the orange one are the peripherals of that. Judging from the chemical perspective, but the peripherals of those blue particle is not enough. So they are very active, which means that actually they are going to be totally broken down by oxide, because there will be like the 4 valent platinum. They cannot go back to the most catalytic attributes of the platinum. That's based on our own internal experiment, but let's try to subject that to the customer's POC. It's more objective gauge, right? So in the customer's test, it turns out that there are 3 different bullet points to share with you. First of all, our Jiping catalyst actually it's abiding by a higher standard than the standard adopted by the customers. And second one is that the Jiping slurry is going to be a very comprehensive, in a comprehensive way. It's enhancing the performance of the membrane electrode, the MEA. So it turns out that under some experiences or contexts, it can enhance the performance of MEA. And thirdly, under some contexts, we have to do some customized catalyst to enhance the MEA performance as well. Okay, please refer to the right-hand side. There is an electronic stack done by a North American customer. They have done their own experiment. It turns out based on our metrics and their metrics, it both performs very well. On the left-hand side, this is like the CGM MEA company in China domestically at the 800 microamps. Think about it's about 30,000 K. You find that it's reduced by about an 8 micro voltage, which is much better than a customer's expectation, outperforming their standards. On this page, we have customer C and a customer D. So we are customizing the catalytic solution for them and trying to suggest to them what should be the recipe of the slurry on the left-hand side from the red line to the blue line. So you find that the CGM has been increased a lot. For customers C, we help them to address the pain points while we customize a catalytic solution for them. More importantly, it turns out that in their electronic stack for the 60,000 circles, degradation is only 30%. So the MA declined only by 30%, which is much better than the DOE, for example, standard. So this is a very good, successful collaboration with our customer. This one is not including catalyst. So in this case, what we do is that we totally tell the customers the recipe for the slurry. So you find that it parallel lines. So it's kind of upward in a parallel session. What does that mean? It means that utilization rate of catalyst has been improved. That is to say that a catalytic solution is very viable and successful, and also a lot of effective size of the an amount of the catalyst that could be used. Hydrolysis, PEM. In the acid environment, what we do is usually for platinum, for this metal, we are trying to put it together with iridium oxide. We don't mix them and blend them together. What they do together is to try to synthesize them together. Why do we have to do it? Because you find that the conductivity of platinum is 5 times that of iridium oxide. So actually, metallic iridium's conductivity is about 10 times of the platinum metal. But as the electrode material, think about it as a nanoscale particle, the oxide iridium. You have to lay it out very optimally. You have to design it in a way that will have an optimal conductivity, but it's difficult to do. So that's why you have to dope it with some metal like platinum. What about the polarity? So think about in the fuel cell stack, there are some uneven distribution of the hydrogen. So sometimes in some stack, there are almost 400 like the single cell. So think about the hydrogen flow. Usually, it's not easy for you to distribute it evenly across all the different cells. So on the assembly line, where there is uneven distribution of the hydrogen across the cells, so there it will be a scenario called the antipolarity. That is to say, you don't have enough supply of hydrogen. But think about the 400 cells put together. So whenever there is sufficient hydrogen, if you are providing overdose hydrogen, so the overdose one is going to destroy the structure of the underdose one. So you put the bad guys together with the good guys, and the bad guys is going to pollute the good guys. The same is true for the production of battery cells as well. So in such a context, you have to prevent against the oxidization of the carbon, because think about the electrical current for the cathode is very high. So anode is very high. It's going to oxidize the carbon. You have to provide additional electrochemical reaction to prevent the oxidization of carbon. What are you going to do? Hydrolysis. So think about the the polarity reaction is having the same pattern as the PEM. It's just that they are used at a different volume and different scale. So anti-polarity, you don't need that much amount. So 4 or 5 is too high. 0 point something microgram is enough, or even fewer than that. On the right-hand side, this is some reference. In the year 2010, there was a paper in the experiment, so the iridium oxide is mixed together with the platinum. Why do they have to do it? Like what I said before, because iridium oxide has the issue of conductivity. If you add a platinum in that, so it's going to be enhancing its performance on the right-hand side. So it's LHV. Well, the iridium oxide has the most electronic current, and the electronic current will go up because you add the platinum, because the conductivity is higher, so more electronic current will pass through. Usually, I think about the platinum and the iridium is 1:9 or 2:8. So that's an atomic proportion. But you can adjust the recipe as well. But there's one more thing I would like to emphasize, which is important. So iridium oxide must be make sure that we have to make sure that it's stable, because in the past we call it like a chlorine alkaline dry iridium oxide, drying the iridium oxide, and it's as a juxtaposition towards like the hydrous iridium oxide. So, but if you add the iridium there, metallic iridium, so after you operate it for a long time, and then it has become like hydrous iridium oxide. So these are the issues we have addressed. So what about the customer's POC? There is a client A. They use per square centimeters, actually 1 microgram. But usually others use 4 or 5 times more than them, but they have a great technology, so they can achieve the same performance. They use 1/4 or 1/5 of the amount of others. So we continuously try to test between the mixture of the platinum mixed with iridium oxide. There's another client, they use 2.5 micrograms per square centimeter. So you find that that technology is not as great as customer A, but at least so they can half the usage amount of the PGM from 5 to 2.5, right? That's very important given the price of iridium oxide, very expensive. So this is a civil case used for like civil usages. Think about a hydrogen electrolyzer. We have done some comparison like on MEA. Think about the cathode is the same, but anode, think about the dotted red line refers to the standardized usage. So like 5 micrograms iridium oxide per square centimeters, and the Jiping use only 4 micrograms. We use less than the conventional ones. We need lower required electric voltage, which means that our catalyst is more effective. So platinum black catalyst compared with platinum carbon is a little bit different. There are some difference between the two in the sense that in hydrolysis, we use a platinum black a lot. So that's why in that context, we control that within 4 to 5 nanometer. So this is a Jiping's PEM hydrolysis, our catalyst, I said it before. So the iridium oxide compared with a hydrous one, we have more stable performance. This is accelerated testing and experiment, some data for your reference. You can find that in our accelerated test, there is only 0.1 moles acid to accelerate it. And then the platinum reaches a peak very fast. But if you use a metallic iridium compared with you use a dry iridium oxide, so metallic one can have a longer time lag. So that's delivering the message to see that the faster the voltage will go up, the shorter your lifespan will be. So this is our civil customer as well. Next, I'm going to introduce to you what about alkaline hydrolysis. What about the challenges facing that? So it goes like this. Because generally speaking, the required volume is huge. Think about given the requirement for your productivity. In that case, if you really want to develop certain volume of hydrogen, so you need to have a huge, massive electrolyte. How do you address the problem? Bring down the voltage. So in the same light, so given the same electrical power put in that, so that is to say that you don't need as much battery. And so as a result of that, that can free you up to go for a higher electronic current. I think a very viable solution is as follows. So using PGM, because in our chlorine alkali industry, we have been using that for many years ago. Generally speaking, this has been used in something we call the flash screen. So think about this page. So we call it like a grid or network made from nickel. On the left-hand side, there is no PGM. On the right-hand side, the two pictures include the precious metal. So we are trying to tightly knit the web and the grid together. Based on our technology, we have about 5 to 6 different companies who can do the nickel grid or nickel web structure. And then they can achieve a very decent performance as well. Think about a web or a grid structure about 200 micrometer in diameter. So its slope is very big. So that's why you cannot use a traditional approach to deal with the new problem. So you cannot use a traditional way because its curvature is very big. If given a big curvature, if you use a conventional coating, you cannot tightly knit them together into the internal web or grid. So you are calling for a new physical and chemical and electrochemical method. Think about this customer, so 670 square centimeters on the alkaline electrolyzer. We have done 2 versions of coating for them. The customers are very happy with our solution, so that's why they are still our customers. So this is with a client in their electrolyzer. This is an experiment we performed for them. The factories, the customer performed the experiment. Next one is about the hydrogen industry here in China.
Well, this just represents the predominant trend for Jiping, a lorry company. We did our forecast and our prediction. So as you can see on the slide, there are different numbers with regard to the forecast for fuel cell vehicles in the next couple of years. The demand by fuel cell vehicles for platinum and the proportion of platinum needed by fuel cell vehicles as opposed to hydrolysis, I think the latter represent 4 times higher than the former for a very important reason, because hydrolysis uses iridium, and iridium is rather expensive, so maybe the amount are more or less identical, but because iridium is much more expensive, so you see the second methodology is more expensive. So much from me. Thank you very much.